Hi, welcome back to Chemistry with Mrs. Mays. Today we're looking at net ionic equations. Let's start with writing a balanced molecular equation. So in this example, I have copper sulfate combining with barium chloride to form copper chloride and barium sulfate. The balancing on this one is a little bit too easy because it looks like everything's already balanced. Our next job is to identify the solubility of each substance. So I'll need to look on my periodic table on the back side and find the solubility rules here. So first, let's see, I have a sulfate salt. I don't have a copper rule, but I have a rule about sulfate. Sulfate salts are soluble unless they're with these 6 ions: lead, silver, mercury, barium, strontium, and calcium. And since copper is not one of these exceptions, then I can write AQ here because copper sulfate does indeed dissolve. Now let's look at barium chloride. I don't have a barium rule, but I have a chloride rule. Chloride salts are soluble except when they're with silver, lead, or mercury. So for barium, that's not one of the exceptions. I'm going to write AQ. And now for copper chloride, copper is not one of these exceptions for the chloride, so I can write AQ. But barium sulfate, here's my sulfate rule. Remember, barium is one of our exceptions, so that means this is insoluble. So we write an S for insoluble because it will be a solid precipitate after this reaction occurs. So now I have the balanced molecular equation, and we've identified the solubility of each substance. Our next step is to break apart everything that is aqueous. So that would be these first 3 substances. They're all aqueous. We're going to break them apart into the ions that they were formed from. So the copper and the sulfate get broken apart. On each of the ions, we have to write the charge so that we show them in their ionic form. Without a charge, they're not ions, they're atoms. So copper is copper 2 because sulfate has a -2 charge. So I know this has to be copper 2 sulfate, not copper 1 sulfate. Then I'm going to break apart barium and chlorine. Barium has a +2 charge, and chloride has 2 chloride ions with my 1 barium ion, so I have to put the 2 out front, because there's not such a thing as a Cl2 with a minus charge. That's not a real thing. That would imply 2 ions that are stuck together in a chemical bond. But that's not what we have. We have 2 chloride ions stuck to 1 barium ion. And then copper 2 chloride is going to break apart in a similar way. For 1 copper, I get 2 chloride ions. And then barium sulfate does not get to break apart, so we're going to just write it all together as one thing. So now I have broken apart everything that's aqueous, and all of my ions have a charge. Barium sulfate does not get a charge because I have my +2 and my -2 stuck together to cancel out their charges. Okay, our next step is to cancel out the spectator ions. So that means up here, the ions that are the exact same from one side to the other, those are spectator ions because they didn't do anything. For instance, look at copper. Copper is copper 2 on this side, and it's still copper 2 on the other side. It didn't do anything, so I'm going to cross it out because it didn't change its form. The sulfate, however, joined up with barium to form a precipitate. So these 2 actually did something. They changed by forming a chemical bond between them. So I don't cross out sulfate or barium. But the chloride looks the same from one side to the other. So that's a spectator ion. Chloride was just floating around in the beaker, not really doing anything. Think of spectators at a basketball game. They don't actually get down on the floor and play the basketball game. That would be weird. Like if somebody ran out of the crowd and dunked the ball, it might be cool, but they're not allowed to do that. They'd probably get arrested, maybe. So let's see. If I write what's left, then I'll end up with a net ionic equation. So I have sulfate plus barium turned into barium sulfate. So the net ionic equation is the equation where we get rid of all the extra information and we just focus on what reaction is really taking place. Let's look at a couple of examples. Okay, in example 1, I show a complete ionic equation. That means all of the aqueous things have already been broken apart. Here's my precipitate. The thing that is solid is the precipitate, and that would be iron 3 hydroxide. Everything else is soluble, so we broke them apart into ions already. The question is asking us to identify spectator ions. Those are the ones that don't do anything in the reaction. So it looks like iron combined with hydroxide. So these two actually did something because they turned into the solid precipitate. But the nitrate here didn't do anything. It looks the same on both sides. And the lithium looks the same on both sides. These are our spectator ions. So now that we know which ones are spectators, we can see what's left so that we can write the net ionic equation. So here's what really happened in this reaction. Iron reacted with 3 hydroxide ions to form iron 3 hydroxide. And that's the true equation, or the net ionic equation. In example 2, we have a little bit more work to do. First, we have to write the complete ionic equation, then we'll cancel the spectator ions, and then finally write the net ionic equation. Since I have my solubility already identified, I know which things I can break apart. So sodium's going to break into 2 sodium ions, don't forget to put the charge, and 1 sulfide ion for sodium sulfide. The silver acetate breaks apart into silver and acetate, or your paper might say ethanoate. It's the same thing. And then we get, oh, you know what? This doesn't look balanced, does it? Because I had 2 sodiums here. Let's put a 2 here and a 2 here. And now we're balanced. Okay. So then I need 2 of these and 2 of those, 2 sodium ions, and 2 acetate ions, because this 2 belongs to both ions, since it's out in front. Don't forget to write your charges in. And then silver sulfide is solid, so we're not going to break it apart. Now I'm looking for spectator ions, the ones that look the same on both sides of the equation. So look at sodium, for instance. Sodium is exactly the same. It didn't do anything important. Cross it out. But the sulfur joined up with the silver, and the acetate looks the same on both sides. That's gone. So it's just a reaction between the sulfide ions and the silver ions. Sodium and acetate were just along for the ride. So our net ionic equation is going to show that we put silver and sulfide together to form a new compound. That's it. The sodium and the acetate ions are still just floating around in the beaker, just like they were before the reaction started. Okay, one more example. So this time, we have to use the solubility rules to predict the products and write the net ionic equation. So remember, in double replacement, we're just going to switch the cations. It's the wife swap reaction. So I take my first 2 things and let them swap places. So now sodium's going to hang out with chlorine, and barium's going to hang out with phosphate. Then I have to look on my periodic table for their charges and crisscross them. Sodium's +1, chloride is -1, so this formula looks good. But for barium phosphate, it's a little more complicated. Barium has a +2 charge, so I need 2 phosphates. And the phosphate has a -3 charge, so I have to put 3 bariums. Now let's check our solubility rules. Okay, so for solubility rules, I see my salts of alkali metals, which sodium is an alkali metal. Those are always soluble. I also have a chloride rule. So barium chloride and sodium chloride are soluble. So barium chloride and sodium chloride are soluble. That word soluble means it dissolves in water. So we write AQ, not an S. I know since it starts with an S, it's tempting to write S for soluble, but don't do it. Resist the temptation. Okay, it looks like we can put sodium phosphate as soluble too, because remember, alkali metals are always soluble. So anything with sodium is aqueous, always. Finally, let's look at the phosphate rule. Here's phosphates. Carbonates, phosphates, chromates, sulfides, and hydroxides are insoluble unless they're with alkali metals or ammonia. Since our phosphate in the reactant is with sodium, that one is aqueous, but over here it's with barium, and barium is not an alkali metal. So this one is solid. That's where our precipitate forms. It's insoluble. So that's how we know there's actually a reaction. If you don't have anything that's solid, liquid, or gas, you don't actually have a reaction. If everything is aqueous and just floats around in the beaker, nothing really changed at all. Okay, next we have to write the net ionic equation. So first we break apart everything that's aqueous. I get 3 sodium ions that were attached to a phosphate ion, 1 barium ion with 2 chloride ions, put that 2 out front, and that turned into, oh gosh, we need to balance this equation. Yikes. I need 6 here to match with a 3 and a 2, so put a 2 and a 3, and life is good. Okay, now it's balanced. Okay, back in business. So now I have 6 sodium ions, and I have 6 chloride ions because the 6 belongs to both of these. And then, of course, barium phosphate doesn't get to change. It doesn't break apart. That's what insoluble means. It can't break apart in water. So look out for spectators now. Let's see, we balanced this. So this changed to 6 sodiums and 2 phosphates, 3 bariums, and 6 chlorides. Okay, now let's look. Looks like chloride didn't do anything. Yeah? Here, cross that one out. And sodium also just stayed dissolved the whole time. It didn't change. But these two joined up to form a compound. So that's where our net ionic equation is. 2 phosphates reacting with 3 bariums forms the compound barium phosphate. And there you go. That's how we do net ionic equations.